It's a pleasure to be here with you. I'm going to talk to you today, address the question, did our planet form by chance? We're going to talk about how we think the Earth formed, how the solar system formed, what processes were involved in sculpting the orbital structure of our solar system. And when we introduce a little bit of element of randomness, of chance, how could have things gone different? What could be different, and which things really matter? And so to start off, the key question is, let's imagine Earth formed again, and things were just a tiny bit different. Does it matter, right? How much do things matter? Like, what is it exactly that makes Earth special, or Earth? And so that's kind of a first thing to think about. And there's a really nice book written about 20 years ago called Rare Earth that addressed exactly this question. The authors, Peter Ward and Don Brownlee, asked the question, exactly what criteria are needed to make a planet like ours, a planet where life could exist for billions of years with liquid water on its surface and lots of nice things like we have on Earth. Is this list really long, or is it very short? And so they argued that this list was very long. And so these guys argued that there were many different factors, they called them rare earth factors, that needed to be satisfied in order for a planet to be able to host life for a long time. And so they argued that this planet would need to live in the right kind of galaxy, and not just that, but in the right place within the galaxy. They'd also argued that the planet would have to be about the right distance from its star in what's sometimes called the habitable zone to get the right amount of energy from the star. Not only would the planet itself have to be about the right kind of planet, it would also have to be in the right kind of planetary system. And they argued that Jupiter plays an important role in our solar system by protecting Earth from comet impacts. They also argued, the planet itself has to be rocky with about the right size, about the right composition. It probably should be geologically active with a specific flavor of geological activity called plate tectonics. They argued that you need a nice big moon to stabilize the spin axis of the planet. You need a trigger for complex life, and there were even a few other ones that I didn't list. And so personally, I don't agree with this list. I think that a lot of these things are kind of too specific and really centered on exactly our situation. And so another possible way to reframe this and to make a simpler list would be to just say, well, maybe to make an Earth-like planet that is relatively, special enough, in quotes, I think all you might really need is a rocky planet with some water, probably about the right amount of water. Not too much might not be great. None at all is probably not great, at least for Earth life. And it probably need about the right amount of energy, which does correspond to a planet being about the right distance from the star, since the star is the source of energy. Too close, it's too hot. Way too far, it's too cold. And so somewhere in the middle, it's okay. All right? And so you can say, well, if there's this very simple list for forming planets that might be nice and like our own Earth, this seems like a pretty simple thing to do, right? Most planets should be able to satisfy this criteria. It's not too hard. Well, you don't have to look too far to find problems with this, right? So what could go wrong? All you need to do is look at Earth's closest neighbors, right? The next planet into the sun is not that much closer to the sun. It's Venus. It's a roasting hellhole. It's terrible. It's hotter than an oven on the surface of this planet, right? Then the next planet out is Mars. That's a barren, frozen wasteland, right? With almost no water on it, almost no atmosphere. It's a terrible place to be. And we're right in the middle. We got beaches and pina coladas and stuff. We're in the right spot. So it's not very hard for planets to fail to meet these criteria. And of course, in the context of our whole solar system, this is what our solar system looks like on a very simple layout. And so just to go through it, for those of you who don't think about planets like 8 times a day, the solar system, we got our 4 small rocky planets close to the sun, then a couple of big gas giant planets, Jupiter and Saturn, and further out are the ice giants, Uranus and Neptune. And so the rest of the talk, I'll talk more about how we think our solar system formed, how our Earth grew, and what kind of random elements could have changed things a little bit. So first of all, one way to think about planet formation is it's kind of like cooking a little bit. And so imagine you're making an omelet, as in this example. There's ingredients, there's stuff that goes into making the actual omelet, like eggs and butter, olive oil. And then there's some processes involved in creating the final dish, the cooking and so on. All right, and so using this kind of analogy, you could say, well, in terms of asking the question, about the randomness, the factor of chance in the formation of the Earth, which of the processes involved make a difference to the final outcome? So which 3 eggs you choose from a carton of eggs, if you choose 3 different eggs to make your omelet, it doesn't really matter, right? It's the same omelet, right? No one really cares. Unless you're super unlucky and you get a rotten egg, then that would matter. Exactly how fast you whisk your eggs, that doesn't matter terribly. Whether you use butter or olive oil, that matters a little bit. I'm kind of surprised they use olive oil. That's a little weird, but so be it. Then there's other details like the cooking. What kind of pan you got? Do you cook for 2 minutes versus 20 minutes? That'll make a big difference in terms of the outcome. So these are the kind of questions and how we're going to look at planet formation processes kind of through this type of lens. So here we go. So where does planet formation happen? It happens in disks around young stars. And we know this because these days, with really powerful telescopes, we can see those disks directly. So this is an image of a famous disk, at least famous among astronomers, a disk called HL Tau. And what you're seeing here was basically taken with a very powerful telescope in Chile called ALMA. And what you see is the bright stuff are concentrations of dust, of big dust grains. And the dark rings are where there's just a little bit less dust. And the size of this disk is about the size of the solar system, a little bigger even. And we don't know right now whether there's planets that have already formed here and that are shaping this dust, or maybe the dust is piling up to form the planets now. There's a little bit of debate about exactly what phase of growth we're in this picture. But what's not debatable is planets are forming here right now. It's pretty cool. So this is where the action is. So now I'm going to guide you through kind of the phases of growth, which we understand from a combination of experiments and numerical calculations, a lot of theory as well. And we'll do this in cartoon land, because it's kind of the easiest way to understand it, I think. So we'll live in cartoon land here. So what we're looking at here, you'll see pictures like this a lot. So let me make sure you understand. So the central star, of course, is on the left. And then that gray thing is looking down the pipe, like an edge-on view of a disk around a young star where the action is, where planets are forming. Okay? And these disks are dominated by gas, by hydrogen gas. And they're only about 1% solids, like dust and rocks and stuff. But we care a lot about that 1% because our planet's made out of it. Right? So the very first phases of growth are dust within these disks sticking together and growing up to a certain size. And you can imagine, they can't keep growing like this forever, because if you take 2 grains of sand and toss them together, they don't stick. Right? You can't keep doing this forever. A couple of snowflakes might stick together for a while, but in general, something else is needed. And so what we think happens is this dust starts to drift within the disk, and there can be little pileups. And what happens is if a little dust pileup gets big enough, it slows down and lets other dust catch up to it. And the pileup gets bigger, and then it keeps getting bigger and bigger. And eventually there's enough gravity, enough self-gravity of the dust in that little clump to basically collapse and directly form what we call planetesimals. And planetesimals, these are things that are typically, you think of them like the asteroids in Star Wars. They're big things, 100 kilometers in size. And these are really the building blocks of planets, of all planets. The next phase of growth, staying in cartoon land, of course, is within this disk. Let's assume that planetesimals have formed all over the place. The ones that are really close to the star form out of rock and iron, and further out they have some water. So why is that? It's just a temperature thing. Too close to the star, any water that's around will be water vapor. And past some distance where the temperature gets cold enough, water becomes ice. And ice is a solid and can help with the building of bigger solid things. And so past this snow line, planetesimals and objects have a lot of ice in them. And past there, we also think that the next phases of growth, where things keep growing by planetesimals bashing into each other and also grabbing onto leftover dust, is also a lot faster. And so in this kind of next phase of growth, in the time it takes for, objects that are about the size of Mars or so to form close to the sun, these are, what we call planetary embryos. In the time it takes for things that are, a few percent of Earth's mass to form close to the sun, really, really big things have formed further out. Things that are, 5 or 10 Earth masses, that are, you could think of as being the cores of gas giant planets, or even kind of the scale of the ice giants. And sorry, I don't know if you can see the text too well, because it got a little shrunk, it looks like. So I'll just say lots of words to try to explain that. Right. So anyhow, these are planetary embryos. This is kind of the next phase of growth. And of course, from then on, things keep growing by getting pounded. And as you can see on the right here, planets like Earth grow from just kind of continual collisions of rocky things bashing into each other to grow bigger and bigger. Now, if that happens further out and faster, and really big things can grow, like 5 or 10 Earth mass ball of ice and rock, then those objects have enough gravity to actually gravitationally grab onto some gas from the disk, become ice giants, or if it happens really fast, to become gas giants. And so this is kind of showing the same type of processes can form different types of planets. One thing that's kind of interesting is as these planets grow, they also interact with the gas disk, and the gas disk can push around their orbits. And so this is a process called orbital migration. So once a planet gets big enough, it launches spiral density waves in the disk, and those density waves push back on the planet's orbit and can cause it to shrink, usually to shrink. Once in a while to grow, but usually to shrink. And so what you can see in this animation is the planet is at the center there with the spiral arms coming off of it, and its orbit is shrinking because those spiral arms are basically pushing it inward. All right, there's an exchange of angular momentum between the disk and the planet's orbit that causes the planet to come closer to the star. That's orbital migration. And we'll see that's a really important process. So a key element here is that you might think, well, migration brings things inward. Maybe it just dumps a bunch of planets onto the star. And we don't think that's true because we know that disks, these gas disks where the action's happening, have inner edges. And so once a planet gets to the inner edge, it can't just fall onto the star, it gets stuck there. Another key thing that happens is late in the game, especially for rocky planets, there's giant impacts between planetary embryos where you can have really gigantically energetic impacts that happen. And we think this happened several times on the Earth. And we think that the last impact of that kind was the one that formed the moon. So here's an animation of that process. You can see the proto-Earth is the bigger one on the right, getting bashed into by a kind of another Mars mass planetary embryo. Boom, and there's this off-center collision that, the first time the embryo kind of bounces off, then it comes back and bashes into it again. And you can see there's this long kind of streamer of clumps of rock vapor, and that kind of gets launched around the growing Earth. And in time, that streamer wraps around and becomes a disk, and the moon coalesces from that disk. So that's the best model we have right now for how the moon formed. And so it's kind of cool. The moon is kind of a byproduct of the last giant impact that the Earth had. Another thing that can happen is when a system of many gas giant planets forms, over long times, the gravity causes their orbits to change shape. And sometimes they have orbits that cross each other. And this doesn't usually mean that they'll end up colliding. Rather, they come and have a series of close gravitational encounters. And the typical outcome is that one of the planets is chucked off into interstellar space, and the other one survives on an elliptical, kind of an eccentric, stretched out orbit. And as we'll see, we think this process is really common. And it's a really kind of very violent process that happens late after planets have already formed. So now we can ask the question, I've kind of gone through what we think of as the most important processes that go into forming planets. So the key kind of, things you have to go through to make your omelet. And you can ask the question now, well, how robust or random are these processes? And so what do I mean by robust and random here? So here, robust would be something where a little change doesn't really make any difference. So it's like if you switch out one egg for another egg in making your omelet, it doesn't matter, it's going to taste the same. Whereas things that are really random are things that could change the outcome a lot. Like if you cook your omelet for 2 minutes versus an hour, that'll change the outcome quite a bit. Okay? So here's how I would place those processes on this kind of very simple schematic diagram. So first of all, disks are pretty robust. Pretty much all of the young stars that we can see, where we could find disks, we do see disks. So disks are very common. They don't all look exactly the same. Some have kind of slightly different structures, different masses, slightly different characteristics. But the existence of disks is very common. They're everywhere. There's also indirect evidence that planetesimals and even planetary embryos form systematically. They form all the time. So we think that their formation is pretty robust. Maybe exactly where they form might vary from one place to another, but they form in a pretty reliable way. The next one is forming gas giant planets. That seems to be a little bit more random because we still don't understand exactly which objects should grow into gas giants. There's some obvious trends where we know bigger things that form faster will become gas giants more likely. But it's not clear that there's a lot of wiggle room in terms of the details of which ones are going to do that. The process of migration is even more random in terms of exactly how fast migration is going to happen, even in some cases in which direction it will happen, whether it will cause planets' orbits to shrink or grow. There's indications that in certain situations, planets' orbits can actually grow. And finally, the most stochastic, the most random processes in planet formation are the ones that happen at the end, the ones involving giant impacts. The outcome of giant impacts depends really sensitively on things like the impact speed, the impact angle. And so if things are just a tiny bit different, it changes the outcome a lot. The same thing with dynamical instabilities. Small details in terms of exactly the close gravitational encounters between planets has a huge impact on the outcome, whether it's a very violent dynamical instability or a very relatively gentle one. Right. So now let's use these pieces that we got, and I'll just kind of lead you through the current paradigm, the current thinking about how our solar system formed. And you'll see it's a pretty gentle thing. And the kind of key elements in here that are a little bit random are there's a little bit of migration thrown in and a little bit of instability, although it's a pretty small one. And given that that planet fell onto the sun earlier, we'll see if things move around in the right place. That'll be interesting. So let's start at this phase in our cartoon story, when planetary embryos have already started to form, and the ones close to the sun are pretty small. They're maybe the size of Mars, which is 10% the mass of the Earth, and the ones further out are already big. They're about 5 or 10 times more massive than Earth. So we think that the innermost big one became Jupiter, and Jupiter is kind of a key thing. The formation of Jupiter basically chopped our solar system in half and really was a very important thing. Then Jupiter, we think, kind of started to migrate inward, like we saw. It launched some density waves. It started to go inward toward the sun. And we think that it cleared out a lot of the rocky stuff that was trying to form Mars. And maybe this is why Mars is so much smaller than Earth. Mars is only about 1/10 of the mass of the Earth, and we think this may be why. But, of course, Jupiter wasn't doing this all alone. There were other planets forming further out, and we think that those big icy things migrated inward, got trapped close to Jupiter, and became Saturn and the ice giants. And then, migration has to continue. Jupiter on its own always goes inward. But it turns out there's an interesting migration effect where two planets that are close to each other, where the inner one is more massive than the outer one, can actually go outward. And so that's the case for Jupiter and Saturn. So we think that they actually turned around and went back out. And this is the current story for the early phases of growth. This isn't the end of the story because the gas disk is still there. And then there was a series of giant impacts that formed the terrestrial planets. The idea is there's a series of giant impacts here between the leftover planetary embryos to form the terrestrial planets. And kind of a similar process is happening further out to form the final ice giants. And this is basically almost our final solar system. There was one final event that we're pretty sure happened that especially sculpted the orbits of the giant planets. And we think that there was a small instability in the orbits of the giant planets. And that's really important to explain the giant planets' orbits, the structure of the asteroid belt, the structure of irregular moons of the planets and stuff. So we're pretty sure this happened. But it was a pretty weak instability because, we're still around. So that's, if you wait another 4.5 billion years, then boom, here we are. Here's our solar system. And we're the third planet from the sun with our pina coladas. It's nice, right? So this is the current thinking about how our solar system formed. Right? It's not, and so this is kind of one outcome of planet formation. But of course, now we have thousands of outcomes of planet formation when we think of exoplanets, planets around other stars. So we have some evidence for other outcomes of this process. So what do those look like? Well, I'm not going to go through everything that we know about exoplanets, But there's a couple key points that are different for exoplanets than they are for our solar system. So I'll just go through those. So the first one is one that I kind of already mentioned. And that is that giant exoplanets around other stars have orbits that are very different than in our solar system. In our solar system, Jupiter and Saturn's orbits are relatively wide, and they're not perfectly circular, but they're pretty close. Giant exoplanets tend to have orbits that are either a lot closer in, or more often, much more stretched out, much more elliptical or eccentric. Right? And as we saw, we think that that's because of dynamical instabilities in systems of giant planets. The other thing that's different about our solar system compared to others is that there's a kind of planet that exists around a half or maybe even a third to a half of all stars in the galaxy, and we don't have one. They're called sometimes super-Earths or sub-Neptunes. They're planets that are kind of between Earth and Neptune in size on orbits that are very close to their stars. And so in this image, what you can see is this is a kind of an artist's impression of the now iconic Kepler-11 system that has 6 sub-Neptune planets. And 5 of these planets have orbits that are closer to their star than Mercury is to the Sun. So these kind of planets are really common, and we don't have any. So now let's talk about the role of chance in detail. So what if things went differently in our solar system? You know, what would have happened? What could have happened? And all right, so let's check it out. So what I'm going to do is lead you through a few different cartoon, again, kind of thought experiments about if the processes of planet formation had just been a little bit different, what could have happened? All right, and I'll call these unlucky Earths. Unlucky Earth number 1 is, what if Jupiter had not grown fast enough and there was a lot more migration involved in the formation of the planets? What would have happened is basically a lot more inward movement of material. Instead of becoming Jupiter's core could have plowed through the rocky stuff that was forming the Earth and kind of disrupted it, and instead formed a system of super-Earths. And so super-Earths are really common around other stars. We think that they form by migrating inward and then having collisions and stuff. And they probably often have a lot of water. Not always, but some of them do. And so in terms of, you know, is this unlucky Earth really that bad? Maybe not. You know, maybe it would have a decent amount of water. What is very different is that it would be much closer to the sun, and so it would be way too hot to have liquid water. So it'd be water vapor or maybe high pressure ice, but probably not nice liquid water like we need for our pina coladas. Yeah. All right, unlucky Earth number 2 is similar. Let's just say Jupiter formed, but it migrated inward a lot further. And so Jupiter grows, moves inward super fast through the rocky stuff. And so as we're seeing in slow motion now, as Jupiter would have migrated inward through the rocky stuff, it would have disrupted the formation of the rocky planets kind of completely. But there's still a chance that another planet could form in the system. Right? And so what could have happened is that another planet could still form kind of in the wake of Jupiter's migration. And what's interesting is a migrating Jupiter really stirs up its planetary system a lot. And a planet that forms behind a migrating Jupiter tends to be a mix of stuff that came from all over the planetary system. And so what does that mean in practice? Well, the planet could end up with an orbit that's not that different than Earth's. And even a size that's not that different than Earth's. What would probably be different is that it would have a lot more water. So say 10 to 100 times more. So on Earth, our oceans are on average a few kilometers deep. On this planet, the oceans would be more like 50 or 100 kilometers deep. And, you know, that sounds kind of nice in some ways, but it might be no one knows for sure if that would be bad for life or not, right? There might not be any continents. There might be a layer of high-pressure ice at the bottom of the ocean that would cut off interactions between the interior and the atmosphere, which on Earth regulates the climate. We don't know for sure. It would be different anyway. Okay? Unlucky Earth number 3 is, well, what if the instability in our solar system was a bit stronger? And so, as I said, we think Earth had an instability, but what if it was, you know, we think it was pretty wimpy. We think it involved maybe Jupiter interacting with an ice giant planet. But we're pretty sure that Jupiter and Saturn never scattered off each other, because if they had, things would be a lot different. So in this kind of unlucky Earth number 3, we kind of assume that that did happen. And what if Jupiter and Saturn had actually scattered off each other? Well, what would have happened is Saturn would have been ejected, and Jupiter would have been stranded on a very eccentric orbit like we see for many exoplanet systems. And in the process, all of the rocky stuff that was forming Earth would probably have been dumped onto the sun. That's not such a great outcome. The best case scenario in this situation would be that Earth was lucky, in quotes, and came a little too close to Jupiter and was actually thrown out and ejected into interstellar space. Because that's probably a little better than getting dumped onto the sun, even though neither is ideal. All right, unlucky Earth number 4 is not really that unlucky. It's just a little bit different. So what if Earth had just grown a little bit faster? What would be different about it? Well, maybe it would have migrated a bit, but let's not talk about that for the moment. It might have grabbed onto some more gas from the disk where it was forming and become kind of like a sub-Neptune, a mini Neptune kind of planet. All right, so maybe instead of having 1 bar atmosphere of nitrogen and oxygen, we'd have 100 or 1,000 bars of hydrogen. Right? What would that do? Well, it would be a lot different for the chemistry of the surface of the Earth, of course. Would it be so bad? People are thinking about this right now, whether this is the kind of thing that would be tolerable for life or not. One thing that would be a super bummer is that you couldn't see the stars, right? Stars are pretty cool. But, we don't know exactly how unlucky this is. It would be different, and it's not clear whether that's bad or not. Finally, the second last unlucky Earth situation I'll talk about is one that starts from the present day. Instead of looking back to when Earth was forming, it starts right now and looks to the future. And so it was shown in the 1980s by Jacques Lascar, who's a French astronomer who's in Paris, actually, that the solar system, particularly the orbits of the inner planets in the solar system, are chaotic. So you can't predict exactly where they'll be in the distant future. There's a window beyond about 10 or 100 million years from now, beyond which you can't reliably predict the exact positions of the planets. To study their future evolution, you have to do it in kind of a statistical way. And it's been shown that due to random fluctuations and chaos in their orbits, it's possible that there could be instability among the rocky planets in our solar system in the future, so our future. And the odds are not very high. They're about 1% chance, but there's about a 1% chance that before the sun becomes a red giant in 5 billion years, that something like this could happen, that there could be collisions between the rocky planets. And here, I just drew it so that Mercury bashes into the Earth and Mars bashes into Venus. But exactly which happens is up for grabs. But there's a 1% or so chance that this will happen in the next 5 billion years. Right? That would be pretty unlucky for us because we already have life. We're already in a pretty good spot right now. This is one way we could end up in not such a good spot. And finally, the last kind of unlucky situation I want to talk about is really not unlucky at all. It's just different. So you can imagine, because of random chance during the formation process, maybe there's a lot of ways that Earth could just have been a little different. Maybe a little bigger, a little smaller. Maybe because of the final impact being different, our moon would be different. Maybe you would have 2 small moons instead of 1 big one, or no moon at all. Maybe Earth could have formed significantly faster or even slower. That would affect its internal heat budget, which would affect things like geological processes. It could have formed a lot wetter or drier. And it could, as I said kind of in passing, be more geologically active or less. And there's other factors like this. Maybe our magnetic field could be different. Maybe other things could be different about the Earth. And it's a kind of a question whether, which of these factors is really important, which ones really make Earth, Earth. And that's a key question to have in mind when we look for exoplanets that are like Earth. And you've probably heard announcements in the press of Earth-like exoplanets, right? So what does that mean? So this diagram shows kind of the planets we know right now that are, in quotes, Earth-like. So on the y-axis is the type of star that the planet goes around. Our sun is, something like 6,000 degrees or so. It's a yellow star. A lot of these are around colder red stars. And on the x-axis is the amount of energy that each planet receives from its star. So you can see the only planets we really have pictures of are the ones in the solar system up there. All the others are artist's impression. And I don't have an answer to this question, but it's a very important question to ask. What does it mean to be Earth-like? These planets are clearly about Earth's size and have a similar energy that they get from the sun. Their sun is Earth, but are they really Earth-like? And this is something we're studying, and in the future, when we can measure more things, we'll have more empirical ways to address this. But it's a key thing of what goes into this, Earth-like thing that we like to call things. Right. And again, this feeds back into what I brought up at the beginning. You know, when we're looking for these planets, do we just need them to be about the right size, on about the right orbits, and maybe have a little bit of water? Or perhaps the list really should be longer, and there really should be a lot more criteria that are needed for a planet to really be thought of as, you know, Earth-like. And finally, going back to our cartoon planet formation or omelet formation recipe, right? If these are all the steps in planet formation, then you can say, well, in the end, it kind of comes down to which of these omelets would you actually want to eat? And you can see, I just grabbed these off the internet. You know, some of these look like omelets, right? The one on the top left, and the middle, and the top right, maybe. There's some that are eggs. You know, I'd eat those eggs even though they're not an omelet. But then there's a rotten egg there. There's a taco. Why is there a taco there? And then there's the thing on the right-hand side. That's just a pan with 3 tennis balls in it. So you don't want to eat that, right? And so I will stop there. I just listed here funding agencies that have funded my research over the years. My blog is called planetplanet.net, and there's a little snapshot of the cover of my book of astronomy poems. So I will stop there, and thank you for coming.
Vous nous avez expliqué vers la fin que vous aviez trouvé des planètes qui ont la même taille, à peu près même orbite, etc. de la Terre. Déjà, il y en a combien? Il y en a beaucoup, il n'y en a pas tant que ça. Et après, comment vous pouvez percevoir si elles sont similaires à la Terre, c'est-à-dire l'eau, pas l'eau, des températures acceptables, pas acceptables, de si loin et par télescope? Comment on fait ça? Comment on peut...
Ah oui, c'est des très bonnes questions. Donc c'est un champ d'études qui est très riche et très actif en ce moment. Donc on connaît, j'ai pas le dernier chiffre en tête, c'est quelque chose comme 30, 40 planètes qui sont environ la taille de la Terre, qui reçoivent à peu près la même quantité d'énergie de leur Soleil que nous on reçoit du nôtre. Donc ce qu'on veut savoir en prochain, c'est comme vous dites, est-ce que ces planètes ont de l'eau? Est-ce qu'ils ont des atmosphères? Ce genre de questions. Et à ce jour, on a presque les moyens de répondre à ces questions, mais pas tout à fait. Donc avec des nouveaux télescopes, par exemple le télescope spatial JWST, qui sera lancé peut-être l'an prochain, on pourra répondre à ce genre de questions. Donc pour l'instant, on connaît très peu d'informations. On connaît la taille de ces planètes et on connaît leurs orbites. Donc ça, c'est 2 critères qui sont importants, mais pas les seuls pour avoir la vie. Et comme je disais, on ne sait pas s'il faut avoir 10 autres critères ou seulement 1 ou 2. Au moins, on veut rechercher de l'atmosphère et de l'eau pour chercher des planètes où il pourrait y avoir de la vie, au moins comme sur le nôtre. Mais bon, c'est là où on est maintenant.
Vous parlez de 6 scénarios. Pourquoi le scénario d'aujourd'hui où nous sommes est le seul possible? Est-ce que les autres scénarios étaient envisageables? Ou est-ce que c'est justement le hasard? Enfin, voilà. Ou est-ce qu'il y a un déterminisme pour être là aujourd'hui à vous parler dans ce micro, quoi?
On n'a pas une réponse qui est entièrement satisfaisante à cette question. Donc quand on modélise la formation du système solaire, on essaye au mieux de trouver des processus et des modèles qui peuvent reproduire statistiquement les planètes que nous avons sans devoir dire « Ah ok, on a jeté les dés 100 fois et par hasard, cette fois-ci, on est comme ça ». Et on y arrive moyennement. Donc on pense qu'il y a certaines choses systématiques qui ont dû avoir lieu. On pense que Jupiter a dû se former assez rapidement et couper le système en 2. On pense qu'on n'a pas de super-Terre dans notre système, probablement grâce à Jupiter. Donc ça, on pense que c'est quelque chose de systématique. Par contre, le hasard des dernières phases de collision, ça, je pense que c'est juste par hasard qu'on a notre système à nous. Donc c'est un mélange des deux.
Quand on pense aux conditions d'émergence de la vie, on a tendance à considérer que la vie sur Terre, c'est l'exemple parfait de la planète habitable. Et quand j'y réfléchis, moi je me dis qu'on n'est pas forcément le cas le plus probable. Alors, on est les seuls enfin, on sait qu'on est là, mais on est là, les seuls représentants. Mais par exemple, il y a beaucoup de petites étoiles froides qui sont infiniment plus nombreuses que les étoiles de type solaire, qui ont aussi des planètes et qui ont un cycle de vie beaucoup plus lent, qui laisserait plus de temps à la vie d'émerger. Et je me dis qu'on n'est peut-être pas les meilleurs représentants de ce qu'est une planète habitable. Je ne sais pas ce que vous en pensez. Mais...
Oui, c'est une bonne remarque. Oui, ça c'est vraiment dans ce que j'essayais de décrire. Quels sont les vrais critères les plus importants? Je sais qu'il y a pas mal de monde qui pense que les étoiles froides sont pas les meilleures pour la vie parce que l'évolution très précoce de ces étoiles est celle que ça prend pour les étoiles de très faible masse. Ça prend 100 millions d'années ou même plus, même 1 milliard d'années pour atteindre la séquence principale, donc pour devenir une vraie étoile, entre guillemets. Donc, et avant ça, elles sont plus lumineuses. Donc, par exemple, une planète qui va être à la bonne température pour avoir l'eau liquide doit subir une phase de 100 millions d'années ou 1 milliard d'années pendant lequel c'est trop chaud. Donc, peut-être que ça perdra tout son eau. Et il y a plein d'autres processus qui vont dans ce sens-là, et on ne connaît pas vraiment les réponses. Donc, pour moi, c'est très intéressant de réfléchir à tous ces cas et de les modéliser, mais à la fin, on n'aura pas une réponse vraiment claire avant d'avoir un autre exemple de la vie. Mais c'est une bonne remarque, merci pour ça.
Conférence vraiment très intéressante, donc qui répondait à la question la Terre s'est-elle formée par hasard? La conférence a montré que la réponse ne peut pas être oui ou non, qu'en fait il faut pouvoir déterminer ce que ça signifie que la Terre se forme. Donc pour cela il faut bien montrer que qu'est-ce qu'on entend par la Terre. Donc est-ce qu'on veut quelque chose qui soit exactement comme la Terre ou est-ce qu'on veut quelque chose qui soit à peu près comme la Terre? Quels sont les critères qu'on va choisir pour que la Terre, pour savoir si la Terre s'est formée? Donc, la science répond par cela par la méthode contrefactuelle, c'est-à-dire qu'elle va envisager tout un tas de scénarios possibles, utilisant les règles et les lois de la physique qu'on connaît, pour voir si parmi tous ces scénarios, lesquels permettent de mener à quelque chose qui est approchant, satisfaisant ou pas. Et donc, ce qu'a montré la conférence, c'est que parmi tous ces scénarios et tous les paramètres qui vont émerger et que les chercheurs vont découvrir au fur et à mesure de leurs recherches et dans les simulations, on va voir apparaître quand même parmi ces paramètres un caractère de robustesse ou d'aléa qui, du coup, peut permettre de donner une notion de chance ou de hasard, dans le sens où certains paramètres, s'ils sont modifiés un tout petit peu, changent radicalement le résultat final. Et si d'autres sont modifiés un tout petit peu, ils changent peu le résultat final. Et donc, la conférence nous a bien montré que, suivant ces paramètres, la formation du disque d'accrétion, les orbites dynamiques chaotiques ou les impacts entre planétésimaux, suivant ces paramètres, ça nous permet d'avoir une idée approximative des probabilités mises en jeu. Mais donc ces probabilités sont toujours énoncées en fonction des critères qu'on s'est donnés à la base. Donc merci encore pour cette conférence très intéressante.
Merci beaucoup.